Okay, so now after we've done permutation, in this lesson we're simply going to talk about combinations, the number of ways of choosing R objects from n distinct objects. And the formula we're going to borrow is the one you learned in first year under binomial expansions. So here, one thing is clear, the order is not important. We can follow any order that we want. So I want to choose, so you notice under permutation, we're saying n permutation R, but here we're saying it's strictly going to be n choose R. Yeah, so the formula is different because the previous formula for n permutation R was just what? Was just n factorial, then we had n minus R factorial, right? Then here we're saying n choose R. So the number of ways that we can arrange R objects from n objects is this. That's what we said. Then here the number of ways that we can choose R objects from n objects is this formula here, the one that you had in first year, which is here. So it's R factorial n minus R in brackets with a factorial. That's what you have. Even on your calculator, it's written. There's a button that has n choose R. There's a button that has n permutation R, to just show that there's a difference between permutation and combination. And here, the sampling that is done without replacement. So when we pick something, we don't replace it back. These are the two conditions for combination to happen. Yeah, so the total has to be 4, and we have 5 girls and 6 boys. That's what we have. We need to find the probability that the team contains only one boy, right? So the total number of people that we want to pick is 4, and the total number of outcomes, the sample space, or rather the population, is supposed to be 11. When you add 5 plus 6, right? So it's like your n choose S, your sample space, is going to be 11 choose 4. That's what you need to know. We need to establish this first. So you can write it as 11 choose 4, right? That's what I'm going to write. So let me try to work it through here. So example 1, solutions. Yeah, so we have 5 girls and 6 boys. So giving us a total of 11, and we need to pick a total of 4. That's what we need to do. So the sample space is simply 11 choose 4. That's what we need to do to get. And the first one, they're saying only one boy. So meaning the probability of picking only one boy is equal to, so we're going to say from the 6 boys we pick one boy, right? Then we multiply it by, from the 5 girls we pick 3 to make a total of 4, right? Then the total sample space is just going to be 11 choose 4. That's what you're going to do. So we need to solve each of these separately, but then since you guys are allowed to use calculators, you can just punch this. 6 choose 1, you get your answer. How many ways can you choose one thing from 6 things? It's 6 ways, right? So you get your answer to be 6. Then 5 choose 3. How many ways can you choose 3 things from 5 things? That's going to be 5 choose 3. You can punch it or just straightforward use your formula, which is going to be 2 factorial there. That's going to be 5 by 4 by 3. 3 factorial. Then there's a 2. This goes, that goes. This gives us a 10. Then 11 choose 4. You're going to get 11 choose 4. That's going to be 11 factorial. Then 4 factorial, and 11 minus 4, that's going to give us what? 7 factorial. That's going to be 11 times 10 times 9 times 8 times 7 factorial. So that the 4 factorial, 4, 3, 2. Then there's a 7. The 7 goes. This is 4, 8. That's 8 goes. 3 there goes, 3 there goes 3 times. This is going to give us 110. That's going to give us 330, right? Yeah, so if you punch this, it's going to give you 2 over 11 to be your answer. Sifi, are you following with what we've done here?
Yes, I am.
Modesta, is this okay? Is it making sense? So if I give
Then
you,
but
where are we doing what?
why are we in that part for the girls?
Oh, so we want to make a total team of 4, right? That's what we want to do, Modesta. So now the condition here per question, only one should be a boy from the 4. So a team of 4 is chosen at random from 5 girls and 6 boys. So we need a total team of 4. So the condition here is that from the 4 people that we want to pick, 1 has to be a boy. That's where the 6 choose 1 is coming from. Meaning the 3 are supposed to be girls, right? So that's where the 5 choose 3 is coming from. Over the total, which is 11 choose 4. The next one also should be easy to think about, because they're saying we need what? 2 boys and 2 girls. So this is going to be straightforward as well. Just say the probability that you pick 2 girls and 2 boys is just going to be you picking 5 choose 2. So you pick 5 choose 2, and also you pick 6 choose 2. Then the total is you 11 choose 4. Yeah, so then you get your answer this side. So when you punch this, your final answer should be 5 over 11 as well. So you guys are allowed to use calculator, so you can just punch this. Yeah, but if you don't want to use your calculator, you can go the traditional route by using the formulas too. This here just means 5 factorial. You have what? 2 factorial, then 5 minus 2 factorial, then get your answer. Yeah, but for the sake of time, we'll just go direct here, and the answer here is supposed to be 5 over 11. So now think about this here. Modesta, is this okay? Is this okay now? What we're doing here, 5 choose 2, 5 choose 2, because of the question, they're saying 2 boys and 2 girls, right? So we need a total team of 4. So already wakwana kudala, because we have 2, 2. It's going to be 4. Is this okay here, Modesta, right?
Yes, it's okay.
So same applies with this one. Look at this here. Number C, they are saying at least 1 girl. So at least 1 girl, it's either we have 1 girl and 3 boys, or we have 2 girls and 2 boys, or we have 3 girls and 1 boy, or they're all 4 girls. That's what we have when they say at least, right? That's what we need to consider. Yeah, or 4 girls. Or the alternative way is you just finding the probability of you getting a boy, and then say 1 minus not having a girl. So let me just put it here. Okay, so C, the probability of having at least 1 girl So here we're going to say it's the same as 1 minus the probability of not having a girl. That's the easiest way you can do it as well. So what is the probability of you not having a girl? So this is the same as 1 minus the probability of you not having a girl is what? Is going to be because there were what? There were 6 boys, right? So 6 choose 4 multiplying 5 choose 0 over 11 choose 4. So this would be 1 minus, this is 15 over 330. So this gives you your answer here. So at least 1 girl, like I said, is the same as you saying what? There are 4 girls. So we can actually do it another way. Let me show you the method I was saying. Or another alternative where you could have done this is saying the probability of having 1 girl and 3 boys plus the probability of having 2 girls and 2 boys, or the probability of having 3 girls and 1 boy, or the probability of having all the 4 girls and 0 boy. So add all these 4, you get the same outcome. Yeah, so you can check this at your own free time. Just check this. You should get the same outcome as well. At least means greater than or equal to, right? So we need at least 1 girl or more. So these are the possible ways or combinations that can happen for us to have at least 1 girl. Is this okay here, guys? Sif, is this okay?
Yes, it's fine.
Yeah. Then Modesta, it's okay, right?
Yes, it's okay.
Okay, then the next one here is at most. They say at most 3 boys, meaning that's the limit. So it's either we have 1 boy, so at most this is like the maximum, right? So for this guy here, number D, I can just give you an illustration here for D. You can work it as well. You can just say at most you can say the probability of you having no boy at all. Yeah, so meaning they're all girls, right? It's just you just saying 4 girls. Yeah, because like this is the limit at most, meaning less than or equal to. So the other one is the probability of you having 1 boy and 3 girls, plus the probability of you having 2 boys, then 2 girls. The last one is the probability of having 3 boys and 1 girl. At most 3, right? That's what we need. So when you add these 4 probabilities, the answer you should get is what? 21 over 22 as well. So this restriction here is in the word at most. So this is what you're going to get when you punch everything. Yeah, so the same thing, the same representation, in case you're wondering. So here means no boy at all, meaning they're all girls, right? So it's going to be what? All girls, so meaning it's going to be 6 choose 0, 5 choose 4. Then since the common denominator is going to be 11 choose 4, so we can just add everything together at the same time, then put 11 choose 4 at the bottom. Then here we have what? 1 boy, that's 6 choose 1. Then we have what? We have 3 girls, plus then here we have 6 choose 2, multiplying 5 choose 2 again, 6 choose 3, then multiplying 5 choose 1. So sum up everything, it's going to give you back 21 over 22. Then the last one, more girls than boys. That's what you want, more girls than boys. So there are only 2 conditions here. Imagine you just want to pick 4 people, right? So how can you have more girls than boys when you are told to pick 4 people? So it's either you have 3 girls and 1 boy, or they're all girls. The probability of having 3 girls and 1 boy, or the one where you have 4 girls and a 0 boy. These are the only cases where you're going to have more girls than boys. Yeah, then this is going to be what? This is going to be 5 choose 3, multiplying 6 choose 1, plus this is going to be 5 choose 4, then you have 6 choose 0, then over 11 choose 4. You sum up this. This gives you your answer, which is what? Your 13 over 66 when you're done solving it. Is this okay, guys? Sifi, is this making sense? Am I too fast?
No, it's okay.
It's okay. Modestus is okay as well?
Yeah.
Okay, so this is basically what you have. Yeah, so let me go to the next part, which is now conditional probability. Yeah, so this is just on combination. Please notice the difference. That's a key thing here. In probability, you always have to know the difference between the theorems you're going to be looking at, because that's what confuses people. Yeah, so we go to the next part, conditional probability. So conditional probability, just like the word suggests, it's just sometimes we're going to be dealing with events that are affected by the occurrence of another event. So we use a notation that looks like this. So if we say P A / B, we just mean that the probability of the event A given that the event B has occurred. So in short, A depends on B for it to happen. Yeah, like the happening of A is dependent on B happening first. So the conditional probability of an event A given that B has occurred is given as follows. The probability that A intersection B can happen divided by the probability of B happening. Provided, so this condition only holds provided the condition of B is not equal to 0. That's what we have. We come from a background where we talked about mutually exclusive events, but now we want to talk about these guys here, which is conditional probability. So for them to have an intersection, meaning they have something in common, obviously, right? It's like how you use street sets. So let me give you an example. So suppose we roll a die once, and we say we need what? Let A be the event that the number that has turned up is even, right? That's what we have. And then B is the event that the number that has turned up is greater than 3. So we roll a die once, right? Now you know a die has how many faces? 6 faces. So now it's either you have 1, 2, 3, 4, 5, 6, right? So let's list these conditions here. So A is that the guy that has turned up is even. So if it's even, meaning you're going to get how many numbers here are even numbers. So there's 2, 4, 6, right? Either a 2, a 4, or a 6 has turned up. Then B, we're saying the number that has turned up is greater than 3, strictly greater, so meaning it's either have 4, 5, or 6, right? So what is the probability of A given B? So it's going to be the probability of A intersection B over the probability of B, right? So what is the probability of the intersection? How many things do they have in common? How many numbers do they have in common? They have, this is what? It's 4 and 6, right? 2 numbers that they have in common. So 2 over 6 divided by, what's the probability that a number that shows up is greater than 3? There are only 3 numbers, so that's going to be 3 over 6. When you solve this, this gives you what? This gives you 2 over 3. That's the probability that A happens given B. Are you following, guys, here? At this point here, Sifi, is this okay?
Yes,
that's fine?
fine.
Okay, yeah. So if this is fine, we can say we can create something general. So the way that you're going to be studying these theorems is that we look at the theorem based on 2 events. Then if it holds for those 2 events, we're going to generalize it for a major larger set, or rather a bigger sample space. So there's a theorem after this definition is given to say if it's true that the probability of A given B can hold, and we say this, A intersection B, there's a general statement that comes in to say, okay, meaning the probability of B is actually the same as if we cross multiply. How can we say this? Like the intersection, rather. Yeah, so we can say when you cross multiply, you say the probability of A intersection B is actually equal to the probability of B, then probability of this. This is what we can say. This is a general statement. Now, this is going to be generalized for as many sets as possible. So this is nicely written in your notes here. So here is the theorem that makes a general statement of what we've observed. They're saying for any events A and B, their intersection this is just how I was deriving it for you here. When you cross multiply, this is what you get, right? When you cross multiply and make the probability of A intersection B to be your subject this side, this is what you get. So now they are generalizing the statement to say for K events, there is A1, A2 up to AK, their intersection, the probability of their intersection is equal to the probability of the first event times the conditional with the previous one. It's just going to be like that. They're going to be, it's like we are connecting them. It's like going to be like a chain like this. Yeah, it's just going to be like a chain. That's the reason why we have this. So if there's need for this theorem to pop up next, we're going to use it. I'll refer back to it. But the only important thing you have to take away here is this same thing that I've given you here. Yeah, this is the only formula that you may need later on for calculating things, and yeah, other examples you'll be looking at. So look at this question here, this example. They're saying if the probability of A given B is 2 over 5, and the probability of B is equal to 1 over 4, and the probability of A is equal to 1 over 3. Find the probability of A intersection B, right? The probability of A intersection B, we say is equal to the same as the probability of what? The probability of B and the probability of A given B. That's what we call it to be. So B is given to be what? B is given to be 1 over 4. Then this is going to be given as 2 over 5, right? So if you multiply this is going to give you 1 over 10. Is it 1 over 10? Yeah, I'm getting a 1 over 10. That's what I'm getting. Hope everyone is okay with this. I'm just using this formula, guys, here. This is the formula I'm trying to use. Yes, because we have this and we have that. So that's how we're supposed to get the first guy here, this one there. Then the next one, they are specifically saying we need to get the probability of B given A. So the probability of A given B here, the probability of is it the same word? B given A. So it's B given A. It's supposed to be the probability of B intersection A and the probability of A. Now we know to say intersection is what? Commutative, right? This is the same as the probability of B A intersection B. It's one and the same. Down you have the probability of A, right? So you can cross multiply here. So we already do have the probability of their intersection, which is 1 over 10 from getting it. The probability of A, well, we have it. It's what? It's 1 over 4. So you have 1 over 4 down there. So you have 1 over 10 divided by 1 over 4. This is going to be 1 over 10 times. Pardon? The probability of A, oh, it's 1 over 3. Yes, thank you. 1 over 3. Yeah, so it's 1 over 10 divided by 1 over 3. Yeah, so this is going to be 3 over 10, right? Yeah, this is going to be what? 3 over 10. Based on this, yes. Thank you for that correction. This is supposed to be a 3 here. Is this okay, guys, here? Can we proceed? Sifi, can we proceed? Okay. Modesta, we can proceed? Okay. The next example is here. Let me just go to, okay, these are the same ones as I got. Okay, the next example as well. Here they're saying X and Y are two events such that the probability of X is 2 over 5. The probability of X given Y is 1 over 2. The probability of Y given X is 2 over 3. Find their intersection. So find the intersection, the probability of Y, and then find their union. So we'll start with the first one. So the data given. So the data given is that the probability of X is equal to 2 over 5, and the probability of X given Y was 1 over 2, and the probability of Y given X is 2 over 3. So the first one, they want the probability of their intersection. So this is pretty straightforward. So we say since the probability of X given Y is equal to the probability of X intersection Y over the probability of Y. Now we don't know the Y as well, the probability of Y. So, but we do know to say the probability of what? The probability of Y given X is equal to the same thing, the intersection, because we say Y intersection X the same as X intersection Y, right? Yeah, so for the sake of just the number, the event which is the one determining the whole thing. So probability of y given x, meaning down here the probability of x, right? Yeah, so we are now going to be replacing the probability of y given x is 2 over 3. The probability of their intersection, probability of x is 2 over 5. Then here we cross multiply. So it's going to be the probability of x intersection y is equal to what? Is it 4? That's same as 4 over 15, I think. Is this part okay, guys? Anyone who has a question here? Modesta, it's okay?
Yes, it's okay.
Yeah, so here on top, in case you're wondering, we said that the intersection is commutative. So y intersection x is the same as x intersection y. No wonder we're sticking with this. Yeah, then the next question is saying we need to get the probability of y. So now we're going to use the other condition. So the probability of x given y is equal to the intersection that we're from finding over the probability of y, right? So meaning the probability of y is just equal to the probability of the intersection over the probability of x given y. So the intersection I'm from finding is 4 over what? 4 over 15 divided by the probability of x given y is a half. Yeah, so this is just going to be 4 over 15 by 2 over 1. Is it? Yeah, 2 over 1. We'll do the multiplication to be 8 over 15. This is what we're going to get. Hope this is okay here, guys. Yes.
Joy is asking to be joined.
Oh, okay. Joy. I can't see her request. Okay, let me just a minute. Okay, so
So use probability of x plus probability of y minus the probability of x equals x1.
exactly. So they want us to get the probability of x union y. There is no condition whatsoever. They didn't say these are mutually exclusive or anything. So we use the formula we learned at the beginning when we were starting the topic. So this is going to be what is required of us. So we need the probability of x, which is already given in the problem, which is 2 over 5. Then we need plus the probability of y. We got it, which was what? Probability of y was it 8 over 15? So the probability of the intersection, we got it. It was 4 over 15. What do we get when you punch all this on the calculator? Let's see. So this part here, you're going to get what? The total, the common denominator is 15, right? That's going to give us 5 into 15, that's 3. 3 by that, that's 6. Then plus, this is 8 minus, that's going to be 4. That's going to give us 4 plus, it's what? 10 over 15. 5 there is what? 2. 5 there is 3. Yeah, so we get 2 over 3, right? Yes. That's true. That's correct. Any questions here? Sifi, is this okay up to this point?
Yes, it's fine. Something with the company.
Pardon?
I'm saying, is there any question something to do with the complementary x?
So now look at this example here. Let's just try to solve this example, then we proceed to look at other definitions. Yeah, then we continue. Yeah. So this example here says a bag contains 4 red counters and 6 black counters. A counter is picked at random from the bag and replaced. So here we're dealing with a replacement type of selection. It's random selection with replacement. Yeah, that's what we have. Then A counter is picked at random from the bag and not replaced. Yeah, so it's not replaced, without replacement. A second counter is then picked. Find the probability that the second counter is red, given that this first one is red. Then here they are saying the second counter is red, given that the first is black. Both counters are red. The counters are of different colors. So here, look at what you have here. So I'll just explain it from the solution here that was given in your book. So they decide to use R1, the event that the first counter is red. Then R2, the event that the second counter is red. Then B1, the event that the first counter is black. B2, the event that the second counter is also black. And they create a tree diagram. This is without replacement, by the way, right? So we have 4 red and 6 black. So we have 4 red and 6 black. So if we create this, yeah, the first one, red 1, then B1 here. So if you are choosing a red one at the beginning, it's supposed to be 4/10, right? Then this is supposed to be 6/10 at the beginning. Then if you pick another red one, that's going to be R2. Then this is B1. Is it? Yeah, the first black ball that you choose. So here we're having what? If you already chose 1 red, right? Then there are going to be 3 remaining. So from the 9, this, then 6 black ones. Then this side, it's supposed to be what? This is supposed to be, the second ball is black, right? Yeah, the second ball is black. So that's here R1, R2, I mean. Yeah, the event that the second counter is red, that's R2. The event that the second counter is black is B2. So this is going to be what? 5/9, then 4/9. So these are what we have. Yeah, so now the first question here is they're saying we need to find the probability that the second counter is red. The probability that the second counter is red. The second counter is red, so that's R2. Given that the first one is also red, that's what? R1, right? That's what they want. So this is just going to be the same as, we pick it from this tree diagram. It's easy, straightforward. So what's the probability of R1 and R2? So this, the R2, R1, is it? Yeah. So we pick it from here. Where do you get R1 and R2 at the same time? They're here. So we're going to get, given that what's the second counter, the answer is going to be this, supposed to be 1/3. How do we pick a second red ball? How much is the probability of picking a second red ball? Given that the first one, so this is a route that we are taking. Yeah, so the first one is already red, so we're coming like this. How do we pick this? So this is what we are picking. Or rather, so the answer is supposed to be 1/3, or rather 3/9, now reduced. So if we were to work it out, they're saying R2, given that the first one is red as well, we're supposed to get what? We're supposed to get R1 and R2, then over the probability that we have R1. That's what we're supposed to do. But here it's just straightforward from this. We can just pick it directly from here. So the answer is this guy here. So whenever it's possible for you to draw a tree diagram, it's easy to evaluate because you just pick it according to the condition. So apanchizungu chabe, guys. Even look at the next one here. They're saying the second counter is red, given that the first one is black. So you go here. Where is the first one is black, the second counter is red. So answer is supposed to be what? 4/9. That's all. What's the probability of you picking a red counter as a second pick, given that the first ball is black? So we're using this route. This is the path that we're taking. So meaning our destination is this. Yeah. Then they're saying the probability that both counters are red. So meaning you have to pick red, right? So both counters are red, meaning we want to look for the intersection. Yeah. So the probability that both counters are red, meaning we have red 1 intersection red 2. Now this is the same as the probability of having red 2, probability of having red 1, given that red 2 has already been picked, right? So here we're going to get red 2, we already have it. It's 1 over 3, which is 3 over 9. Then we multiply it by you getting this. This was what? This gave us, was it a 4? Was it a what? It's a 4 over 10. Yeah, the first, this guy here. The probability of you picking a first, the first boy is red, given that the second boy is also red. It's just going to be this. 4 over 10. So this gives you your answer. When you multiply, that's going to be your 4 over what? Your 4 over, is it your 4 over 30? Or am I making this? Probability of picking, both counters are red. So I'm saying probability of picking red 2 and red 1. So I can write it here. Yes, the probability of picking red 1, and the other one, the second one, is also red. So this is going to be the probability of you picking a first red ball and also picking the second red ball, given that the first one is also red. So this is going to be the probability of you picking a red one at first is 4 over 10. The probability of you picking a second red counter when the first one was also red is 3 over 9, which is a 1 over 3. And now from here we can have 2 there is 1, 2 there is what? This is 2 over 5, multiplying 1 over 3. This is where the 2 over 15 is coming from. So this is what you get. On C, they're saying both counters are supposed to be red. Yeah, now remember we have the probability that the first here, both counters are supposed to be red, so meaning the first counter is here. So let me just say here directly, red. So how do you get the probability of red? Maybe let me just use this logic for the normal logic for probability. What's the probability of picking two red counters, red 1 and red 2? You just multiply 4 over 10 times 3 over 9. That's the answer you're going to get. Is that okay, Sifi? It's just
yes,
direct.
that's fine.
Yeah, that's fine. So sometimes it's just here, like here, the only unique restriction we had was that there is no replacement. Yeah, even if they are using this language for given that, making it all conditional, we can still go direct to the usual ways of calculating probability whenever you have a tree diagram. So even the next one, look at the next one. They're saying the counters are of different colors. So meaning we're going to only have the two choices. It's either you have red, black, probability of having red, black, and black, red and black, or the probability of having B1 and R2. These are the only conditions that you have. Yeah, so we just need to get this. Multiply 4 over 10 times 6 over 9. 4 over 10 times 6 over 9. That's what you need to do. Then plus B1, which is 6 over 10. Then times the red one is 4 over 9 again. So just get your answer here. Your answer here will be 8 over 15. So just the usual probability that you learn. The only restricting here, the only thing that is restricting here is that there is no replacement when you pick the counters. Yeah. So in short, the second event happening has been affected by the event that happened first. So R2 is dependent on R1. Now, because we used a tree diagram, we already did the subtraction. Now you're seeing that the denominator is 9 here when it was 10 at the beginning. So we already took the condition into consideration. Now we can just go direct the way we are doing here. Yeah, so hope this is okay. Joy, is this okay? Oh, it's confusing. Okay, yeah, so I know you missed the first part of the lesson, but it's okay. Just that's Kasemka formula. That's the only thing we talked about here. Yeah, to say the probability of an event A given that B has already happened is just given by this formula. Now we start playing around with this formula here. Now I had said probability of A intersection B is the same as the probability of B intersection A. They're one and the same because of the intersection being commutative. Yeah, then from here you can cross multiply. Either you pick this or that version. So I decided to pick the first version. Then here when you cross multiply, the other formula we can make up from here is that A intersection B is actually the same as probability of B, then times the probability of A given B. Yeah, so this is what we have. Now the next theorem, before we look at the bias theorem, there's just an intermediate theorem here. They're saying if events A and B are independent, so we talk about independent events. So if events A and B are independent, so A and B, if they're independent, it means that the probability of A intersection B is just equal to the probability of A times the probability of B. That's how we treat our independent event. And you need to note that their properties, the probability of A given B is just the same as the probability of A. Also, the probability of B given A is just the same as the probability of B, because they don't depend on each other. So the probability of A given B is the same as the probability of A, because A happening does not depend on B. Yeah, so this is a property whenever we talk about. So in case you're wondering, where is this all coming from? So this is coming from, this formula here is actually coming from, recall, I'm just from saying that if you have probability of A intersection B, it's equal, probability of A given B, it's equal to the probability of A intersection B over what? Over the probability of B, right? Now from this formula here, we're saying independent events, this is the formula, right? Their intersection is equal to their multiplication, the product. So on top here, I can just say probability of A intersect, and then the probability of what? B, right? Down here I have probability of B. So you're seeing that the B can cancel just to give me probability of what? Of A. So that's why we're saying probability of A given B is equal to probability of A for independent events. Yeah, that's what we have. Now let me explain a little bit about things to do with complements. So see if you are saying, how about we do things that have the complement here? So these the following properties are also valid. Before I give you an example, so there are these other properties that you need to know as well. Again, A and B are independent. So provided these guys are independent. So here we're saying if you have, if A and B are independent, it means that A and B complement will also be independent. That's what it means. Then it also means that A complement and B will also be independent. That's what you need to take into consideration. Then it also means that A complement and B complement are also independent, provided the bigger sets A and B are independent. And this is going to draw us to the following derivation. So you can derive the fact that the probability of A intersection B complement is the same as the probability of A minus the probability of their intersection. This is the fourth thing. Fifth property is that the probability of A complement intersection B complement is the same as 1 minus the probability of A, the probability of A union B. Yeah, because you can take the complement outside, right? From here, this is the same as probability of A and B with the complement outside. So it turns out to be this. Yeah. then already know what this is, so you can just replace as well. Yeah, so this is just, these are some of the properties you're supposed to know whenever you're dealing with independent events. So hope this is okay. Yeah, so again, like I said, whenever we learn a property, we extend it to several other sets. So everything we've talked about here can be extended to a series of sets. So if you have a list of sets, we're saying if you have a bunch of sets, let's say you have k events, meaning you have, let's say, a1, a2 until you reach ak, the kth event, and these guys are independent, or rather mutually independent, for every event that you have here, meaning the probability of their intersection until you reach the last event, which is that, is the same as their multiplication. So remember the property I'm from giving you here, this guy here. Yeah, we're saying their intersection is equal to their product, right? Now we're extending it to say it doesn't matter the number of events you have, it will still be true. So even if you have 10, there will be their product here. So that's what I want to write here. It's going to be the probability of A, the probability of A2, the probability until we reach the last one, which is the probability of AK. We just multiply them. Yeah, that's what this rule here says. Yeah, so maybe let me give you an example. They are saying, this example is very interesting. They are saying A is thrown twice, so a die is thrown twice. That's what you have. They are going to be three sets of events that we're going to consider. So we're going to consider that the first throw results into a 3, and B, we're saying the total is 7. Then we're saying C is the total is 8. That's what we have. So we toss, or rather we roll a die. This is a die, right? This is a die that we're dealing with. See, yeah, it's a die. So we throw it twice. So you're going to have the following. Let's call this example. Yeah, so you know a die has 6 faces, so let's just make this 1, 2, 3, 4, 6. Okay, so let's say we throw our die, right? So this is the operation we'll be dealing with. Yeah, so the operation we're dealing with is a plus. That is a plus, not multiplication. The operation here is going to be a plus. One, 2, 3, 6. So this is what we're having. So look at this. When we toss a die this side, look at the guy we're having. So this is either one of these faces can tear up, right? Same applies here. This is like the second toss. So here let's say the second toss. And here this is the first toss. Yeah. Then the operations that we're going to deal with here is that we're going to sum them. So let's say here it's a 2. The addition here is what? This is going to be a 3. That's a 4. That's a 5, 6, 7. It's going to be 3, 4, 5, 6, 7, 4, 5, 6, 7, 8, 5, 6, 7, 8, 9, 6, 7, 8, 9, 10. That's going to be 6, it's going to be what, 7, 8, 9, 10, 11, 9, 10, 11, 12. Yeah, so this is what we have. Now the first question is saying the first row, the first results into a 6, right? So first row results into a 3, that's event A. So event A, probability of event A happening is 1 out of 6. That's one thing we need to have, because we have how many faces? We have what? We have one face from the 6 faces. That's only a 3, right? So that's what you can have. Then probability of the event B happening. They say the event B is what? The total being 7. The total being 7. So how many times do we get a total of 7 between the first toss and the second toss? So we're going to get what? 1, 2, 3, 4, 5, 6. From 36 chances, right? So we're going to get what? We're going to get that's going to be 6 over 36. That's going to be 1 over 6 as well. The sum being 7, right? That's what we have. Then the next one, the total is 8. So if the total is 8, again we check it. It's going to be 1, 2, 3, 4, 5. Yeah, so it's going to be 5 over 36. That's the probability of C happening. So we need these guys in place. Probability of C happening is 5 over 36. Let A be the event that the first throw results into what? The first throw results into a 3. Yeah, so what's the probability of you having 3 turning up when you toss a die? There are how many possible outcomes? There are 6. And how many 3s do you have? There's only one face that has a 3. So that's the reason why it's 1 over 6. Is this okay?
Yes, it's okay.
Yeah. Then here they're saying are A and B independent? Yeah, so if they're independent, meaning they shouldn't have any intersection, right? Meaning their intersection, this must be equal to what? 0. So you know to say the probability of A intersection B is supposed to be the same as the probability of A, or rather, not 0. I mean, independent doesn't mean 0. It just means that we can say this. Yeah, that's what we are from learning about independent events. So we're looking forward to get this. Yeah, so if we multiply these two, what do we get? That's going to be 1 over 36. So this is going to be 1 over 6 multiplying 1 over 6. So this gives us 1 over 36. Yeah, so yes, A and B are independent. So here the answer is yes, because they have the probability of the intersection is this part here. Their what we say, their intersection, probability of their intersection is equal to 1 over 36. So here, if we think about it here, let's say what's the intersection? What is A and what is the total is 7, right? The total is 7, and from the total that we go to be 7, how many times do we get to use 3? So 3 was used to add up with this 4, right? This guy. That's what we have. Then did we also use a 3? Did we also use a 3? And yeah, so we have something there, right? Yeah, so they do have an intersection actually, and we're saying the intersection A and intersection B is the individual probabilities, which is PA times PB. Yeah, then look at C, A and C. Maybe here you understand what we're doing. Probability of A, we have probability of what? Probability of B we have. Now look at this. Here.
Sammy, I didn't get the way you found question. If for A and B, the one you are just from calculating, I didn't get the way you found it.
For A, we just did this. The probability of P intersection, the probability of A intersection B, we just use 1 over 6 then we just used 1 over 6 here, we got 1 over 36. Yeah, so we're saying this here, since the intersection, the number of times that we use what? The number of times that we use we use 3, because here they are saying the first row results into a 3, right? Yeah, so there's only one time, the first time that we use a 3 to get a 7, a total of 7 is here. We used this 3 and this 4. So the only time where they meet, this is why you are seeing there's like a plus and there's like the multiplication sign. So the only time where there's a 3 is this case. Up, we got 1, 3, 3. Then we are summing them up. The only time where you are seeing plus and x is here. So from the 36 times that we did up this thing, because there are 36 outcomes there, 6 by 6, right? The only time where you see a plus and a cross is here one time. So that's where 1 over 36 is coming from. And it's the same thing we are getting after obeying the independent formula that says the intersection of two independent events is equal to their individual probabilities, and we still got 1 over 6, the same thing as the diagram is giving us. So we're saying yes, it is independent because the probability of the intersection we saw in the table is just equivalent to the multiplication of the two probabilities separately. So that's the reason why we're saying yes, because this statement is true. Is this okay? Modesta, it's okay now? A and B are independent. Now we have to check whether A and C are also independent using the same thing as well. We know that A means that the first row is 3, then C means that the total is 8, right? Yeah, now they are saying, are the two events independent? Yeah, so let's check for their intersection. I'm going to use the table that was already drawn for us here. Yeah, so according to the table, remember we say the event C is that the sum is 8. So when do we get 8? 2 plus 6. That's why you're seeing these two multiplication symbols, these guys here. So this is where all the located 8s are supposed to be. Then the first row is supposed to be, the first row gives us a 3. So look at what we got. So we're only getting one place where 3 gives us 8. So 3 plus 5, that's 8, right? Where we can see a plus and a times. So we are seeing that according to the information in the table, the probability of A intersection B is 1 over 36. But then as we got the following, we got this. We got that probability of A is this, 1 over 6. The probability of C is 5 over 6. So if you multiply the two, multiply probability of A times the probability of C, 1 over 6 times 5 over 36. The answer we're getting is what? 5. Then 6 times 36. What do you get? Anyone to punch this on the calculator?
It's
It's what?
216.
216. Okay.
216.
Okay, so now look at this. You have 5 over 216 and 1 over 36. So they are not the same. That's what we mean. So when we check, that's why you're seeing this to say these are not correlating. So we say A and C are not independent. So this is the outcome that they want us to show. I hope this is okay. See if this is okay.
Oh, okay, yes, it's okay.
Yeah, so this is how they were getting them. So the same applies with the next one. So already know they want us to check whether here, look at this part here. They want us to check whether they're saying find the probability of A union B union C. That's what they want us to do. Now we already have a formula for that. whenever we are dealing with union. So there is something that we learned previously. There is this formula here. I'll just go direct to it. So we said whenever it's union, remember if there are two of them, if it's A union B, remember we said it's going to be the probability of A plus the probability of B, right? Then minus the intersection. That's what we said, because we don't want to repeat things. So now what if there are three of them? So if there are three, we extend the same thing. A union B, then union C. So we have to write probability of A plus the probability of B, then plus the probability of C. Then remove to my individual intersection. So I have to remove the intersection of A and B first. Then again minus the probability of A intersection C minus the probability of B intersection C. So everything has been catered for. Then now bring back the intersection between all the three sets. That's what we need to do. Yeah, because these two mini intersections have gotten rid of the common thing, the common intersection between all the three sets. So we have to bring it back just once. So that's where the plus is coming from. Yeah, so now we have to just plug in. So this has to be equal to that. Probability of A, we already have it. So it's 1 over 6. Probability of B, we got it was 1 over 6 as well. Probability of C, it was 5 over 36. Then minus the probability of A intersection B, we have to go to our table. A intersection B, we got it previously, which is 1 over 36. Probability of A intersection C, so A intersection C, we got it as well. It was negative 1 over 36. Then the probability of we need the probability of, is it B and here we need the probability of this guy here, is it B intersection C? Let's see if there's going to be any intersection. Let's go to our diagram. So our diagram, B intersection C, where the total is 7 and the total is 8. So the answer is 0, right? There is no place where the total is 7 and the total is 8, because these are the two events. B is the total is 7. C is the event that the total is 8. So that cannot happen at the same time. Yeah, so we're going to put a 0. Then there is no place where all the three events are going to intersect. We cannot get a total of 7 and a total of 8 and also get a 3. There is no box where all the events tick. So this is also what? 0. So now we can just work out this. The final answer has to give us something we should be okay with. This is supposed to be 5 over 12, I think, by the time you are done. So here they found the 5 over 12. Are you guys okay with where the zeros are coming from? See if it's okay.
Is it because there's no intersection?
Yes, there is no intersection between A and B. So if there's no intersection between A and B, there can't be intersection between A, B, C. Yeah, because B is that the sum is 7. C is that the sum is 8. There is no box where we have that. We cannot have a 7 and 8 in the same box. Yeah, so that is not happening, meaning all the three sets are disjoint. They're all independent. Yeah, sort of. So yeah, so that's what we have. Then we can go to another example. Just after this, they give you a very short example. So I'm just going to use your lecture notes. So here, look at this example here. Number 2, the one that's written number 2, this is just trying to check whether you've mastered the formula already. Suppose that the events A, B, and C are independent, given that the probability of A is that, probability of B is that, and their union is this. Find the probability of C. That's what they want. Find the probability of C. Now, they gave us a keyword. Keyword here is independent. Independent meaning, if you ever see something like this, meaning this is the same as probability of A times probability of B, right? That's what you have. So now we're going to rewrite a formula for this. So let me just go back here. So they're saying, this is the example, another example. So they're saying the probability of an event A, so probability of A is 1 over 4, and the probability of B is 1 over 2. The probability of their union, A, union B, union C, is equal to, that's a 3 over 4. They want us to get the probability of C. Let's to get this. So we'll say the probability of A, union B, union C is equal to the probability of A plus the probability of B plus the probability of C minus the probability of A intersection B minus the probability of A intersection C minus the probability of A, the probability of B rather, B intersection C then minus the probability of, plus, is it here supposed to be minus? This is a minus as well. Then plus the probability of their intersection, so something like this. So this can be summarized to be, we have this already, their union, the union throughout is what? The union throughout is 3 over 4 is equal to the probability of A, we have it, which is 1 over 4. The probability of B, we have it as well, it's 1 over 2. The probability of C is what we are looking for. Then minus the probability of A intersection B. These are independent events, so it will be probability of A times the probability of B. It's the same thing. Then here it's the same as probability of A times probability of C as well. Again, probability of B and probability of C. Again, then the last one, which is a plus, probability of A, probability of B, probability of C again. We can replace the ones that we can replace. So have our 3 over 4 is equal to, this is a quarter and half. When you add this, that's going to give us what? The same as 2, 2, that's going to give us 3 over 4. Then plus x, probability of C, I'm just going to use x to represent it. Then minus probability of A, we have it, it's 1 over 4. So I'll say 1 over 4x. So this has already been represented. Probability of, okay, probability of what, guys? Probability of B, sorry. Yeah, looking for probability of B, which we have. So probability of B, the probability of B, which is half. Then here we have minus probability of A is 1 over 4. C is when I put this. Then this is going to be probability of B, that's going to be half x. Then plus again half and 1 over 4, then and then x. Yeah. So it's like you're just solving for x, guys, here. I hope this is okay, because when you solve for x, so you notice this goes this side, gives us a 0. Everything here has an x, is it? Does it have an x? Is it? Just a minute. So, because if it becomes 8 again, it will not make sense. So this is going to give us, we have a 3 over 4. No, it's okay. We have this guy here. There was something that should be, oh, there's this guy. So I was worried about everything becoming 0, but this component here does not have x, yeah? So this will go this side, becomes 0. We have this component which turns out to be 1 over 8. Then these components that have x, when you sum them up, they'll give you something like 3 over 8. Yeah, then you have this, you have x here, probability of C. When you multiply this, cross multiply this side, so probability of C just gives you 1 over 3 when you multiply. So when you are done, your x should be 1 over 3. Yeah, so if you're okay with the formula, and the fact that they say that the events are independent, so the parts that have intersection just changes to these parts, then you do a replacement, everything will be straightforward. Any questions on this part? Can we proceed to the last two theorems, then we are done with our class? Any questions, guys? Here, Modesta, Mwale guys, come. Is this making sense? So I'm just going to state the theorem.
Yeah, so there is no other way of solving this question like a shortcut.
For this part, no, there is no other shortcut. You just have to go, because the key thing that is restricting us is the fact that the side, the events are independent. So we have to use the property that if there is a union between all the events given, we distribute them like this using this schema formula. Then we apply the fact that for independent events, the intersections are equal to their products, the individual product of their probabilities. So this has to be preserved. Yeah. Yeah, so hope this is okay. Now let me just give you a definition of the Bayes theorem, because at least we've done combinational probability, conditional probability and combinations. Now let me just state for you and explain Bayes theorem. The rest of the things in your notes are just examples that you can ask me on WhatsApp before the next topic, which is what random variables. Look at this. So we are here. We just got done this part. So now here is the preamble to the Bayes theorem. Then they go in details to talk about it here. So before they give it to us, they give us a preamble, like a baby step to the actual theorem. Then the last things here, all the things you talk about, Kumalas took, all these slides are just like examples, and topic 2 starts, which is random variables. Yeah, so you just have 3 examples that you can look at and ask me if you have questions, if you'll be stuck by WhatsApp. Yeah, because after this, the next thing you see are random variables, which are not part of your quiz. So let me explain the Bayes theorem. I'll start with the baby theorem first, the one that is given before the actual theorem. Okay, so we've talked about independent events. So here on this theorem here, they're saying if we have disjoint subsets that are mutually exclusive events, their intersection, their union will give us back the sample space. Yeah, so we're just saying the sample space, or rather the subsets, are said to form a partition of the original set. Yeah, so here we're saying if you have so many sets, these guys that are disjoint subsets of C, meaning they have nothing in common, they're mutually exclusive. But if you add them up, they'll all give you the original set, which is the sample space. Meaning this theorem is going to be true here if B1, B2 up to the BK set represent a partition of S, and A is arbitrary an event on S, then the total probability of A is equal to the probability of A is equal to the probability of B1 times the probability that A has happened given B1. And also, so let me give it to you here separately so that you see it. Let me give it to you in a picture form. Maybe be able to understand it better. So if you have sets, let's say B1, B2, then you have B3, until you reach another set, let's say BK, right? Now, these sets are disjoint, but their union, when you sum them up, whenever you add them up, right? Like this, at the map union until the last set, they give you the original set sample space, which is S, meaning S contains the events B1, B2, then B3, and so forth until you have your BK. These guys are subsets, though they are disjoint. Now you can pick, so these are simple events. Now you can pick a more bigger set, sort of. Let's say you pick set A, and set A is equal to B1 and B2. A combination, or rather, something that has a subset of S, which is not a simple event. We can always get the probability of A. So the probability of A can be given as the probability of B1, the first event in A, B1. Then we say probability that A has happened given that B1 has already happened. That's what we are saying. Plus, if there's another event here, let's say B2, we say the probability of B2 given that A has happened before B2 has happened. So depending on the number of the events that you have placed in the subset of S, which is in this case A, it will determine how many parts you're going to have on the right hand side here. Now, to shorten this, we're just going to say the probability of A is just going to be the same as the sum of all the probabilities of the B's that you have. Then, so we just put I or J here, and times the probability of A and that I that you have until you finish all of them. So I starts from 1 up to N, or rather K. That's what they write. So this is where this guy is coming from. Sorry, that's where this is coming from, to say, to just generalize this piece, a summary of this. So if you have 3, let's say, you should be able to understand this from what I'm going to write here. So if you have 3 sets in, let's say S is equal to B1, B2, B3, then B4 is equal to BK. Then you have a subset of S. Let's say we make up A to be containing only B1. No, not even B1. Let me start from something that's not B1, in case you're wondering, is it a must that B1 should be there? No. So let's say you have B2, then B3, and let's say B4. Yeah, this is a subset of that. You're seeing that A is contained in S, right? So the probability of the event A is equal to the probability of the first event in A, which is B2, the probability of A given B2, then plus the probability of B3, then the probability of A given B3, then plus the probability of B4 times the probability of A given B4. So this is just the same as a summation from I is equal to 1, I is equal to 2 rather, because starting from 2, 3, 4 up to the 4th one, the probability of Bn times the probability of A and Bn. So this is basically what they mean. Yeah, so a petition is just like a disjoint member. It's like a subset. So it's like we just make a petition, just make a piece, get a piece. So this is what they're trying to explain using this diagram here, to say you can have so many subsets, these guys here, right? But then we can petition. So it started like this first. It started like this. Then from here, the made up pieces, right? The made up pieces started like that. The made up class. So there was like B1. Let's say there's B1 there. Let's say there's B2. Let's say there's B3. Then up to BK. Then from here you make up a subset. Let's say we take this, make this set to be A, which is a subset of S. S is the bigger one. A is eating up the B1, B2, B3. These pieces as well are also included in A. So that's what we are saying. To avoid repetitions, we have that particular illustration. Now this is going to be summarized using this theorem here, Bayes' theorem. So as long as a petition is formed, we can come up with an arbitrary condition so that we don't repeat things, and we say the probability of B happening, given that A has already happened, is equal to the probability of B times the probability of A given B has happened divided by the sum of all the individual probabilities. This theorem is coming from what we are from learning, this for a partition. Yeah, so this here is the formula for Bayes' theorem, this guy here. Yeah, so we're just saying, if you understand the previous case that I was explaining, if you understand this, the sum, the probability of A to be the sum, right? This meaning where there should be probability of A, we can be putting the sum. So meaning in Bayes' theorem, so let's just say it here. I want to make it as simple as possible. So in the Bayes' theorem, we're saying as long as we have a partition S, which is a subset of, as long as we have A which is a subset of S, where A is a partition, so this is a partition of S, is a subset of S, then we're saying the probability of any B you pick, let me say J, given A is equal to this. Remember, this under conditional probability was supposed to be what? The probability of B, this guy, times intersection, rather. Let me take you back to where this is coming from. Intersection, the probability, event A. Then down, you needed the probability of what? The probability of A there. Now, according to the previous theorem, the baby step before Bayes' theorem, we're saying the probability of A is equal to, it's like the sum, right? The sum, according to this up to the K. So we say it's Bi, the probability of Bi, then times the probability of A given that Bi. So this is where the Bayes' theorem comes from. Then the top part we are saying this. Remember, we talked about this theorem, remember? So again, recall we said probability of A intersection B is the same as probability of what? Probability of B times the probability of A given B, right? Yeah, so this is where the top part comes from, to say it's the probability of B, Bj times the probability of what? Of A, yes, of A given the Bj that you have. So this is where the Bayes' theorem comes in. We are mixing two theorems, the previous one and the other one that we talked about earlier on. Yeah, so this is where the Bayes' theorem comes in. Yeah, so hope this helps a little bit. So you have 3 examples to look at before you resort to bed, then you'll be ready for tomorrow. So text me on WhatsApp in case you have any challenges, but you have to look at this. So I would advise you start looking at them right now while the working is still fresh. So you just have these 2 examples. There's example 1, 2, 3 going down in your lecture notes. Is this okay, Sifi?